When you want to generate a uniform continuous random number, two arguments, two parameters are very important: lower bound and upper bound. As you know about uniform distribution, and we review it to some extent last session, when it talks about lower bound and upper bound, it means such a thing: lower and upper. For example, lower can be 10, upper can be 15. After that, you get your uniform distribution like this. Now, in this slide, you see the formula that gives you the uniform random number in the intended range. Now you have rand. Now you have the rand function, but rand function gives you the random number, the uniform random number between 0 and 1. But in simulation cases, that uniform random number can be in any range. So we need a formula that gives us that range. The formula is this: the lower bound, and like the other formulas that we have had so far, it has equal sign. After equal sign, you put the lower bound. For example, if the lower one is 10, you put 10. If the lower one is 5, you put 5. If the lower point is 1000, you put 1000 plus the length of the range. That is upper bound minus lower bound. For example, in this case, that lower bound is 10 and upper bound is 15. The range size, the range length is 5. And you put it here times rand. In that situation, you get your intended uniform random number. Let's do it together in Excel. Let's generate a random number between our intended ranges. Okay, so here we have these lower and upper things here, and here I'm gonna generate, so here I'm gonna put format in okay, so here I'm gonna get the random number with that formula that we discussed. Okay, with what lower and upper bound? Lower, let's put the lower 20 and upper 30. Okay, we want to generate uniform random numbers between these two numbers, or in this range. The formula starts with equal. If you remember, the first thing is the lower number, so I put the lower number, 3, plus the length of the range, that is upper bound minus lower bound, and all these times our lovely rand function. Let's check the results. 28, a random number between 20 and 30. Awesome. Let's try it several times to see if it really works for the other situation. So I'm gonna create these. So 20 random number, and here we are gonna get, we need to freeze them first. So I'm I'm gonna freeze them with dollar. Hopefully you have learned these things in MIS 161. Okay, now it is okay. I'm gonna drag all of them along these 20 rows, and now I have 20 random numbers between 20 and 30, and they are uniform. As you can see, 26, 28, 28, 20, 22, all of them are in that range. So that formula works. Let's change 30 to 40 to see what will happen. You see, now we have numbers that are 34, numbers 35, the numbers that are above 30. Let's make it this 20, let's make 20 35 and see the results. Now you have 20 random numbers between 35 and 40. So as you can see, 36, 35, 36, 36, and all of them. So this formula works beautifully. Now you are ready for this activity. Activity 2. It asks you this. For the case of Sanatronics described before last week, simulate the parts cost per unit 1,000 times. Now you know when it asks you to simulate something 1,000 times, it is equal to generating the random numbers related to that case. So here it says you just need to generate 1,000 random numbers, random uniform numbers between 80 and 100. Why 80 and 100? Because the case that we discussed last week was about this. And I have put the case also for you just in case you don't have access to last week material. So it says Sanatronics decides to describe the uncertainty in parts cost with a uniform probability distribution, the one that we just learned to simulate. As shown in the figure, forget about figure, it is about last week, cost per unit between 80 and 100 are equally likely. So it means it is uniform. A uniform probability distribution is an example of a continuous probability distribution. This means that the parts cost can take on any value between $80 and $100 with equal likelihood. Now, when it asks you to simulate this situation, you just need to generate random numbers 1,000 times between 80 and 100. Pause the video and do it yourself. Here is the answer. You write the formula like this. 80 is the lower bound plus 100 minus 80 times rand. So when you do this, the random numbers that you get should be something around this, and do it exactly in the same way we did it for the normal situation. And by the way, when you want to check if you have done it right, don't forget to calculate the average over 1,000 cases you have generated. It must be the number that it gives you, it must be something around 90, because the average when the lower bound is 80 and the upper bound is 100 is 90. So when your random numbers are correct, when you calculate the average of that 1,000 random number, it must be something around 90. After learning how to generate random numbers that are normally distributed and that are uniformly distributed, now it's the turn for simulating a discrete probability distribution. When you want to simulate a discrete probability distribution, You need to know about two rules in this regard that I'm going to discuss it with you now. Rule 1, more probable the number is, the longer is the assigned. Here we need ed range. So what does it mean? It means that if you are simulating a discrete probability, again, the reason I'm not elaborating on this discrete probability, because we discussed all these things last week. If you are not caught up, go and check last week videos and PowerPoints. So if we have, it is discrete now. It is discrete. Imagine, for example, this one is 10 and this one is 15. The probability of 15, imagine, is 25%, and probability of 10 is 75%. Okay, now when you want to simulate it, you need to assign these numbers that you see here to a range of 0 to 1, because you are simulating. And rand function generates uniform random numbers between 0 and 1. So that's the reason we need to follow this range, because the rand function, as the main engine we have in Excel simulators, generate uniform random numbers between 0 and 1. So now we have this discrete probability distribution with only two values, 10 and 15, and 15 probability is 25% and 10 probability is 75%. So when we want to assign, because now we are going to assign 0 to 1 to these values, how we are going to do this? When we want to do this, it says more probable the number is, the longer is the assigned range. Which one is more probable, 15 or 10? Of course, 25. So which one is more probable? Of course 15. I first wanted to make 10 more probable, but no problem. We can handle it. Let me make it another time. See, because I don't want you to get the impression that larger numbers are more probable. So we have 10, we have 15, and here it is the probability of 10, 75, and here we have 15, that is 25. Nice. Now, more probable the number, the longer is the assigned. 10 is more probable, so the assigned range on this 0 to 1 range must be longer. How much longer? It depends on the probability. The probability of 10 is 75%. The probability of 15 is 25%. So 10 is 3 times of 15 in terms of probability. So the assigned range must be 3 times of the other one. So if I divide this range to 4 quarters, the assigned range to 10 would be 0 to 75%, and to 15 is 75% to 1. So here we have 10 and here we have 15. That much easy. Makes sense, because 10 is more probable. So it claims for longer ranges on that probability engine. So we give 10 0 to 70.75, and we give 15.75 to 1. In this situation, when you generate random number by rand, the numbers that comes can determine exactly according to the probability which one is the case.